Hey, I have introduced conditional distributions and conditional means and other conditional concepts, and they are very important in our analysis in interpreting and defining research questions. For example, you may consider conditional means in this way. Suppose that you want to predict someone's income. So you don't know who he is, who she is. You want to predict income, but the only information you know is her or his education. So you know that she or he has, like say, college degree. You have no other information. Then how would you estimate that? Then when you predict the income, the best estimator is the conditional mean of income given the same number of same years of education. So for example, so say education is the only information you can use to predict the income, then like if you know that she has a college degree, then you may look at the data and filter filter out the college degree holders. You only use the college degree holders and calculate their average, which will be your estimator, your predictor. So that's how we are going to use the conditional mean in later. And it is also justified by this sense. So we also, when we predict, the second task to do is to calculate how big the error is. We have to evaluate how good your predictor is. So then in that case, typical measure of the error, the amount of the error is the mean squared prediction error, which is another conditional mean uh, concept. So I believe we will have a chance to study what this means later. So I'm going to skip it like I will touch it just briefly at this point. So conditional mean, so maybe this would be enough to understand the conditional mean at this point. Okay, then next, the fourth important concept we consider here is the random sampling. So at the beginning of the review, we started from the population, and so far we assumed that the population is completely observed. So you have an infinite number of observations hypothetically, and see what you can do. So if you have that infinite number of observations, then you can calculate the probability, you can calculate the expectation, you can calculate the variance, standard deviation, covariance, correlation coefficient, conditional probability, conditional mean, conditional variance. All of these guys can be calculated. It's just a matter of computation. However, the problem here is all of these are based on the assumption that you observe infinite number of observations. But now, actually, that does not happen. That you never have an infinite number of observations. Or as I said, if you have, you don't need to learn statistics. There is no room for statistics if you have perfect observations. So we have to assume that we have just a part of the population, and as opposed to the population, we call that the sample or sample. So a sample is part of the populations that you observe, and that's your data. And we assume that the sample is randomly chosen from the population. It is not biased to a certain direction, but it is randomly chosen. So it's simple. From the population, you choose a unit, an object, one by one at random. So choose one person and replace back to the population and choose again and then repeat that many times. So then, the selection is random, because the selection is random, the observations, the random variables are random. Because if you chose a different person, then you would observe different outcomes. So, so redoing an experiment will yield different outcomes. That's the basically what we uh, define as randomness. So, however, this is a subtle difference. Before you randomly choose a person and observe the outcome. Before doing that, before the experiment, the random variable can take any value. The value of the random variable is not determined, so it is random. However, once you observed the outcome, it is not random anymore. It's determined, so it does not change. So it was originally random, but your observations are not random anymore once they realize it. They realize. So later, the distinction between realized outcomes and random outcomes, unrealized random outcomes, make some differences later. So when we get there, I will remind you again. In notation, we usually use subscript 1 through n or I to index. So yi is the outcome, the value of y for the ith chosen individual or unit. So you repeat. So choose one person, and the outcome is, so you randomly choose one, say one adult, and his income is y1, and choose another person, and her income is now y2. Repeat that many times. Then n is the total number of repetitions, randomly choosing a person, and yi is just a representative notation for ith observation. Y is the value. So it is, remember, this notation is useful because it is random. It does not show it does not tell you what is the realization. So it means it is still random. So later it will be realized and it will be determined, and then it will not be random anymore, but notation itself is useful to represent it is still not realized. And there are two important assumptions for a sample to be random. So when we say a random sample, or when we say we are doing random sampling, it means it satisfies two conditions. First, when you choose two, for example, when you choose randomly choose individuals, the individuals must be independent of each other. So the first person you randomly chose and the second person you randomly chose should be independent. So for example, just choose one person, number one, and say there was a friend next to him, and choose the friend as your number two. It is wrong. That is not random. The friends would be correlated to each other in some sense. So that may be biased. That is not random, for example. And second condition you have to satisfy is that y1 and y2, the individuals you randomly chose, must be identically distributed. They must be from the same population and the same distribution. In other words, say some of the observations are of totally different nature. Say you randomly choose. Suppose that your target is man, but if your sample includes a woman, it's wrong because the woman's distribution may be different from man. So your choice, your random samples must be identically distributed. They must be of the same nature, or must be from your target population. So simply independently distributed and identically distributed is abbreviated to IID. IID assumption is the most famous assumption in statistics. So identically and independently distributed. So we say like this: yi, the set of observations yi, where I ranges from 1 to n, and this set the elements of this set are IID. So independent and identical distribution. That's what it means. Okay, so far we have briefly reviewed the basic concepts of probability theory. So that was the first part. And this is 1/3 of eco320. I have finished. You have taken 1/3 of 320. So in what follows, we are going to discuss the other 2/3 of 320 in a week. So I hope you now you kind of remind yourself of what you learned and you recall the concepts. And if you are still not sure if you learned it, then let me know or ask me questions or ask me for help. These are important concepts. We are going to use them for sure later. So make sure you understand them. Okay, I'm going to continue the next section, estimation section, right away. Bye.